Okay. So, we want to find the extremum points of the functionals, that those which we discussed in the last section. The problem is little more difficult because the domain of our functional is a space of all paths. Now, this is an infinite dimensional space. We can put some sort of a vector space structure on it, but when we put vector space structure on it, it is an infinite dimensional vector space, and we need to sort of do some sort of a calculus to find the minimum of the functional or maximum or extremum, whichever case that may be. Now, what I will do is I will begin with a simple ideas from the ordinary calculus. You see, in case of ordinary calculus, if you have a real valued smooth function defined over some segment of real line, then within that domain the function has a stationary point if its first derivative is 0 at that point. Okay. So, for an example, the stationary point can either be a minimum or a maximum or an inflection point. In this example, we have a minimum at point D and we have a minimum at maximum at point C, or there is also a minimum at point A because it is a boundary of the domain. Okay. We are of course not interested in the points like A and like B where there is a minimum and a maximum respectively. Our interest is in the stationary points where the derivative, the first derivative of the function becomes 0, and which is what happens at point C here and point D here. And in this case, when we find a point which is stationary, then of course we look at the second derivative to decide what kind of point it is, whether it is a minimum or a maximum or an inflection point. By inflection point I mean take an example of x cube, and the derivative of x cube, which is 3x square, will become 0 at x is equal to 0, but the second derivative is also 0, and the function here neither has a minimum nor has a maximum. Okay. It temporarily stops rising or lowering at that point, but then it continues to rise in the positive side. Okay. Now, what we are going to do is look at the same idea in a slightly different way. So, if I look at the Taylor expansion of this function about x naught, then I will get f at x plus epsilon will be equal to f x naught plus epsilon times f prime at x naught and plus all the terms which have epsilon square and higher orders, okay, higher powers of epsilon. But because x naught is a stationary point, the derivative of function is 0 at this point, and hence this term here is in fact 0. In that case, I am only left with the constant term plus the terms which are quadratic in epsilon or higher, and then I will define a variation or delta f x, delta f calculated at x naught as f at x plus epsilon minus f x. Now, if epsilon is small enough, then this would be approximately 0. So, at x naught, if you take small epsilon, the small change in the function is 0. In other words, the function just does not change, and that in fact is the meaning of the word stationary, that it ceases to either rise or lower at that point. So, we will put that in a neat statement. So, at stationary point x naught, the variation delta f is 0 if you vary the point by small infinitesimal amount epsilon about x naught, about the stationary point. And this is the idea that we want to generalize to the other dimensions or to higher dimensions. So, look at the case of 2 dimensions. In case of 2 dimensions, I have taken a simple function here, which is x square. So, z is equal to x square plus y square. So, the plot is that of z is equal to, and it is a function of 2 variables. Okay. We want to use the same idea. We know that at x is equal to 0 and y is equal to 0, that is at the origin, we have a minimum of the function, which you can easily see here. Okay. We can visually inspect. But if I want to generalize the previous idea, what I need to do is I need to go away from that that stationary point by infinitesimal amount and look at what happens to the function. If it does not rise or lower, it remains stationary, or the variation is 0, then I would call this as stationary point. But which direction? So, here I have mapped one direction, which I called as n cap. So, if I go in the direction of n cap, the value of function should not change. But why this particular n cap? No, it must happen for all possible n cap, and there are infinitely many directions. So, you have to check in all directions whether the function remains stationary or not. So, I will define the stationary points for 2 dimensional case as if the variation delta f at x naught y naught, which is of course defined now like this. So, the nx and ny here in this expression are the 2 components of n cap vector. So, what you are doing is you are actually travelling along the direction of n cap, and I multiply it by an infinitesimal number t, and then calculate the variation by taking the difference, and this must be 0, but the key point here is that it must be 0 for all possible directions there. So, all possible nx and ny, the function must remain stationary. Then we will call x naught y naught as a stationary point of the function. Okay. Let me apply that to the problem that we have here. So, if I wanted to calculate, so this procedure of course we will use to also find the minimum points. So, suppose I take a variation here. If I take variation, then delta f will be equal to, so we will take x plus t times nx whole square plus y plus t times ny whole square. Okay. And then do a simple expansion. Here of course, the Taylor expansion is straightforward. So, sorry, minus x square minus y square, that is f at x y, and this immediately will come to t times, so 2 t x n x plus y n y plus all the terms of the order t square, and this must be equal to 0. Okay. When will this be 0? Since t is some arbitrary infinitesimal number, this must be 0 for all values of nx and ny. So, I will write that condition. So, condition for stationary point here will be x nx plus y ny must be equal to 0, but must be true for all nx and all ny. And now, you see what happens here, because they are true for all values of nx and ny, I can of course in particular choose nx to be 1 and ny to be 0, and what does that immediately give us? That tells us that x must be 0 and Similarly, if I choose nx is equal to 0 and ny is equal to 1, that gives us y equal to 0. There you go. We have found the point at which the function is stationary. So, function has a stationary point at 0 0, and this true for every nx and every ny is crucial part of this argument there. Let me take one more example. Now, this function is, so I have the same definition here, but this function here is in fact e to the power minus x into 1 minus y square. If you visually inspect this graph here, you can immediately see that there is no minimum anywhere or no maximum. Is there a stationary point? No, there is no stationary point either. So, let us look at whether we can find. So, let me take one point which is on the, so here is the x axis and this one here is y axis. So, let me choose one point which is on x axis. So, if I choose a point which is x comma 0, okay, and we want to find out whether there is a stationary point here. Now, do the same thing, calculate delta f. So, your delta f becomes, so it is e to the power minus x plus epsilon, then plus multiplied by 1 minus y So, let us calculate the delta f again. So, delta f here will be equal to e to the power minus x plus t times nx and into 1 minus y square. So, here y will become y plus t times ny whole square, and we want to retain only the linear terms here. So, I will write this as delta f is equal to, this is e to the power minus x, and the e to the power minus t times nx, because t is infinitesimal, I will retain the linear terms which is 1 minus t times nx, and then on this side you have 1 minus, so minus e to the power minus x into 1 minus y square, and you have 1 minus y square minus 2 times t times y times ny, and plus of course the t square terms which I am going to ignore. So, minus e to the power minus x into 1 minus y square, and this will simplify to. So, out of this, the first bracket 1 into 1 minus y square, this of course will cancel with, and what you are left with is e to the power minus x. Then because we are looking for linear terms in t, so there is t and there is nx, and plus you have, so nx into 1 minus y square minus 2 times y ny, okay. And of course, there are all the other terms which are in t square. And now look at this, must be equal to 0. This immediately tells us e to the power minus x is never 0, t is not 0. So, this bracket here must be equal to 0. So, nx for x y to be a stationary point, nx multiplied by 1 minus y square minus 2 times ny must be equal to 0, and remember this must be true for all nx and all ny. And in particular I can of course choose nx is equal to 0 and ny is equal to 1. This immediately tells us that y must be equal to 0, y coordinate definitely must be 0, and if I choose ny to be 0 and nx to be 1, this immediately tells us that y must be equal to either plus or minus 1, and these two will never simultaneously satisfy. Do not satisfy, which means any point in this entire plane actually is not a stationary point. If you choose y is equal to 0, which comes to a point like this, you can see that if I travel along the y direction along this contour, then on that contour along that path the function is stationary, but passing through the same point, but now take this path and the function is not stationary, okay, which means the function of course is not stationary in this case. Now, in 2 dimensions of course you can have variety of stationary points. One is of course minimum, one is maximum, and you can also have what is called as saddle points, and saddle points are very easy to visualize. If you have seen a horse saddle, on the horse saddle you have a maximum on one side, and along the axis along the direction of the body of the horse you have the minimum. Okay, this is called as a saddle, and also the points which have this kind of behavior. Remember, this is also a stationary point, but this particular point will be called as a saddle point. Okay. Now, what we want to do is take this idea to further more dimensional spaces. If you have n dimensional space or a domain, what would happen? The situation will be similar to 2 dimensions, except in 2 dimensions I had x axis and y axis. In n dimensions maybe I have n axis x1, x2 and so on, and then I will vary nx1, nx2, nx3 and so on, and if the point has to be stationary, then in the n dimensional path you would be travelling along an arbitrary direction. The definition will look same, except nx and ny would now become n1, n2 and so on, and then the variation of the function as you travel along any direction, but by infinitesimal amount, the variation in the function should be 0. Okay. All right. This is the idea I want to use in our functional minimization program. So, here I have these 2 cases. In the functionals case, the domain is infinite dimensional and every point in the domain is actually a path. It is a function of functions, remember. So, what is the meaning of varying or going little bit away from the given path? So, here in this diagram I have a blue path there, and I want to look at all possible paths which differ from this blue path infinitesimally. And how do I do that? Exactly the same way I did in the earlier case. So, I will take this y naught, which is a blue path, then add to it some eta x. So, your blue path there is y of x, sorry, y naught, and I want to take the variations about y naught. So, what I will do is I will take a infinitesimal t, multiply it to arbitrary function eta and add it to y, and you can see in this animation that as you change the value of t, you get paths which are nearby. Okay, as long as t is infinitesimal, you will get paths which are nearby. Now, this is like going in one direction. How do I go in another direction away from y naught? Here, now you just change your function eta x to something else. So, this is eta 1 x, and what we are doing is to the same y naught, we are adding eta 1 x and see what happens. Now, we also get paths which are nearby y naught, but they are not the same paths as covered in this diagram. This diagram and this diagram both have variations which are different from each other. And how many ways you can do this? You can do that in infinitely many ways, because you see, if I want to get a new path, all I have to do is add some arbitrary eta x to it, and this arbitrary eta x, because the endpoints are fixed, whatever eta that we add, that of course must be 0 at endpoints. So, eta must be 0 at endpoints. As long as eta is 0 at endpoints, I can multiply it by infinitesimal value and add it to y naught. I get an infinitesimal path which is near y naught, and this is the idea of variation that I am going to use in finding the stationary points of the functionals. Okay. So, let us extend this definition. Here I have written the definition already. So, the functional is already defined as j, and which is between all the paths which pass through x 1 y 1 and x 2 y 2. And we will say that, so eta is some arbitrary, remember, some arbitrary function with endpoints equal to 0, or value of eta at endpoints is 0, and then we define j is said to be stationary at y naught at given path if the variation, that is delta j at y naught. And how do I define the variation? Variation would be calculate action at a nearby path which is y naught plus t times eta x minus the functional at y naught, and the difference of these two should be 0. And remember again, this must be true importantly for any arbitrary eta that satisfies these conditions. As long as that happens, then we call it as a stationary point. See, eventually what we were interested in was to find a minimum of the functional, or in probably some cases maximum of the functional, some extremum, but for the functional to be extremum, the necessary condition is that it must be a stationary point. It is not a sufficient condition, remember, but it is a necessary condition. So, if we find a stationary point, then we will go ahead and check whether it is minimum or maximum or none of them, okay, and whether it fits the requirement that we had. So, we might find we are looking for a minimum, we find a stationary point, but it turns out to be a maximum, then of course, we have to discard that and search for the minimum again. Okay. So, now let us apply this. If I want to apply this to the functionals of our interest, and remember the functionals of our interest were of this kind. So, j of y of x, we defined it as integral over x from x1 to x2 of some integrand which depends on y, y dot and x. Remember here y dot is dy by dx. Okay. So, when I take a small variation, then what happens to the integrand? Let us look at that first. So, if I take y of x which is equal to y naught of x plus t times some eta x, then that means the variation in the path at each point, the variation of the path at each x. If you want, I will go back to the previous one. Remember, at each x, at each value of x, I have this delta y, okay, and this is what we are going to call it as delta y of x. So, delta y of x is nothing but t times eta x, and I can also take the derivative of this with respect to x, then y dot of x is going to be y 0 of x dot plus t times eta dot of x, and this immediately means that for the function y dot, the variation in y dot is in fact simply equal to t times eta dot of x. And let us look at now what happens when I change the path. The y dot also changes, and then eventually the integrand would change. So, the change in the integrand would be delta f will be equal to the partial derivative of f with respect to y into delta y plus partial derivative of f with respect to y dot into delta y dot. Of course, we are looking at the variation at each x. So, basically the third term, because it depends on x, will not appear here. This is similar to the virtual displacements that we talked in our first week. Okay. So, let us substitute various quantities there. So, this would be equal to del f over del y into t times eta and plus del f by del y dot into t times eta dot of x. Okay. Now, let us go ahead and put this back into the, so your delta j x, this will be equal to integral from x1 to x2, and all I have to do is put delta f there, which still is function of this dx. Okay. Now, let me do that. So, delta j at y of x will be equal to integral from x1 to x2, and now I am going to write this slightly differently. So, there is a t which can be taken out, and there is a del f by del y and plus into eta plus del f by del y dot into d by dx of eta dx, and this term here can be integrated by parts. So, this will be integral from x1 to x2 t times and del y. I am going to write eta outside, so I will leave it for the time being, and write the second term of this integration by parts. That would be equal to integral of, so this would be d by dx of del f by del y dot into eta, and now I will put that eta outside and write it like this. Okay. Now, what we get? This is integral from x1 to x2, and remember this bracket here is some function of x del y dot, and then there is a t eta dx. And I am going to use an identity here, I am going to use an identity here from the real analysis. If I have integral from some a to b of some smooth functions, and if this is equal to 0 for any function g, then f of x must be equal to 0 identically over the domain. And you see here, remember this, for y naught to be a stationary point, this must be equal to 0, and if this is 0, this must be 0 for every eta x, and that immediately tells us that the quantity in the bracket here, like this one, this must be equal to 0. So, del f over del y minus d by dx of del f over del y dot must be equal to 0. So, for y of x to be stationary point or stationary path of j, the condition is this equation here, and this is the equation which is called as Euler-Lagrange equation. Oh, you can immediately start noticing the similarity between this and the Lagrange's equations we derived in the first semester, first week. And not surprisingly so, because when we are going to define this functional as a action for a mechanical system, the integrand is L. So, all that will happen is that this equation will in fact actually look like Lagrange's equation for a mechanical system. Okay. So, but here of course, they are in the variational calculus, these equations are called as Euler-Lagrange equation. And note that these or this equation here is in fact second ordered differential equation. So, what we have done here is this, just like in case of ordinary calculus, to find the minimum of the function, we actually get a condition in terms of the derivative. Here we have got a condition for the path which becomes stationary or at which the functional becomes stationary. The condition is in the form of a differential equation. Okay. Now, because this is second order differential equation, there are of course a few special cases where integrating this equation is actually quite easy, and one of the two conditions is, if your integrand is in fact independent of y itself, but then from the equation itself you can immediately see that d by dx of del f over del y dot then must be equal to 0. On the right hand side you have del f by del y, and because f is independent of y, this would be the case, and this immediately tells us that del f by del y dot must be equal to some constant. And this is the first order differential equation. So, this is equivalent to integrating your second order differential equation once, okay, and this quantity then would be called as first integral. Or the second case where things are easy is when your function or integrand f is independent of x. Okay. If this is independent of x, then clearly d by df by dx, remember this is a total derivative of f with respect to x at the stationary point, will be equal to partial derivative of f with respect to y into d by dx of y plus del f over del y dot into d by dx of y dot. And because it is independent of x, the partial derivative of f with respect to x is 0. Now, for the stationary paths, I immediately know that del f over del y, this term is in fact nothing but d by dx of del f over del y dot, and then you have y dot, this is y dot, and plus del f over del y dot into d by dx of y dot. And you can now see that this just looks like a product formula for derivatives, and we will write it as d by dx of y dot y dot, and this gives us d by dx of f minus y dot into del f by del y dot is equal to 0. That immediately gives us the first integral of this equation, and that would be f minus y dot into del f by del y dot must be equal to constant. Okay. So, there are these two special cases in which actually find or doing one integral is immediate, and the second case or this identity here is called as Beltrami identity. Okay. So, now we are equipped with procedure for finding minimum or maximum of the or stationary points of the functionals. Let us look at some of the examples. As our first example, I will look at the same problem which we had in our classic concrete sand puzzle, but there also we needed to find a path which was the path of the shortest distance. The path of the shortest distance there from the point A to point B in that example, or in that case it being a Euclidean plane, we already know the result. We know the result that the path must be a straight line path, and that path will have the shortest distance between the 2 points. Now, this problem of course can be more difficult if this space is not Euclidean. For example, on the surface of the earth, when you go from Delhi to London, the distance measured over the surface of the earth, that is not same as a straight line path which will go through the earth. Okay. So, there the in case of the non-Euclidean geometries, the path which gives you the shortest distance is called as a geodesic. Now, I will take this example only for a Euclidean space, and in the assignment I will ask you to do the example of the earth's surface. So, here if I take 2 points, this is x1 y1 and this is x2 y2, and consider any path. This is the infinitesimal path segment. Then we know that the total length of the path is integral from x1 to x2 of ds. So, basically you put all the small path segments together to get the total length, and this we will write as x1 to x2, and remember I had written this as 1 plus y dot square to the power half dx. Now, this functional now is in the form that we want, and in this case we identify the integrand function f as 1 plus y dot square to the power half, and which path will give me the shortest length or shortest value for this functional is the path which satisfies the Euler-Lagrange equation. And in this case you can immediately see that f is independent of y, and in which case we already know that the del f by del y dot must be equal to some constant. I will call this constant as a, and let us calculate this del f by del y dot. That is very easy, and that would be equal to y dot divided by 1 plus y dot square to the power half, and this must be equal to a. But this is easily simplified to y dot is equal to, so that would be square. So, yeah, so that would be a divided by square root of 1 minus a square, but that is also a constant. I will call this constant as m, and that immediately gives us dy by dx must be equal to m. This is the first integral. Do one more integral, and that immediately gives us y must be equal to mx plus c, or that. So, it is an equation of a straight line. A straight line would give me the shortest distance path. Now, how do I find m and c? There are two unknowns in the integration, but I also have two conditions, that y at x1 must be equal to y1 and y at x2 is y2. Okay. So, I can immediately find out the two constants there. Now, let me go to a second but little more involved example. This is also the famous Brachistochrone problem, which originally Jacobi has posed as an open challenge to the scientist at that time. Now, in this problem what we have is a wire which is bent in some shape. Okay. The shape is now rigid, and then there is this bead which frictionlessly slides over this wire, and what we are going to do is we are going to drop it from x1 y1 with 0 velocity, and under gravity this simply would fall down. Okay. And as it falls down, it gains the velocity and it reaches the other point after some time t, and that time t we can immediately write down as t as a function of path y is integral from x1 to x2 and its ds divided by velocity. So, you take a small infinitesimal line segment here at x y and then divided by the velocity at that point, that gives you time dt to cover the small distance ds, and then we can get the, after integrating we get the total time. Now, what is the velocity v here? But if it reaches the height y, then of course we know that mgy must be equal to half mv square, because from the top point we had simply dropped it with 0 velocity. Okay. And I am going to assume y1 to be equal to 0, otherwise I would have to write y1 minus y here. Okay. So, this gives us v must be equal to square root 2g times y. Let us put it back in this, and then we get integral from x1 to x2, and then you have 1 over square root 2g, which is only just a number which we can forget about, but in the numerator I have 1 plus y dot square to the power half, in the denominator I have square root y dx. So, now we can identify our integrand. Instead of minimizing t, I will minimize square root 2g times t, which is the same thing. Okay? The same path will be the minimum for both cases. So, here f, the integrand function, is in fact 1 plus y dot square divided by square root y, and you can immediately see this one here is independent of x, which means I can do one integration immediately using Beltrami identity. So, let us write that down. So, what we have is f minus y dot into del f by del y dot. This must be equal to some constant c, okay, and this gives us, so it is 1 plus y dot square to the power half divided by square root y minus y dot, and I will immediately take the derivative here. So, that would be y dot divided by square root of into 1 plus y dot square, okay, and this must be equal to constant c. Okay. So, we can of course immediately simplify this. This will give us 1 must be equal to, you can do this calculation at home, into square root of 1 plus y dot square into c, okay, and then square both sides, rearrange the terms, and once you rearrange the terms, you can immediately get y dot is equal to square root of c divided by y minus 1 or dy divided by square root y divided by square root c minus y integral, and this must be equal to integral of dx, and I will write it as x plus b. Okay. This is the system that we want to solve. Now, the integrand on the left side, this one here, is not very difficult to calculate. I am going to again ask you people to do this algebra at home, but I will give you the substitution. So, if you put y is equal to c times sin square theta by 2 and carry out the integration, in which case you get x is equal to constant c by 2 into theta minus cos theta, and y, remember, was c times sin square theta by 2, but I can also write that in terms of, so y would be equal to c by 2 1 minus cos theta. So, be sin theta. And what is this? This you can recognize is the equation of a cycloid. Okay. And what does the cycloid look like? Cycloid looks like this. If I take a disc rolling on a surface and you mark a point on the circumference, and as it rolls, the point on the circumference will trace a path in two-dimensional space like this one here. So, here you can see that the black dot there on the circumference as the disk rolls will form a curve, and this curve is called as cycloid. And the solution here is in the form of cycloid. So, if I start dropping the bead at x is equal to 0 and y is equal to 0, and I want that particular bead to reach this point here, which is x2 y2, then I will rewrite the solution. X, remember, is constant. I will write c by 2 as r into theta minus sin theta, and y, which is r times 1 minus cos theta. Okay. In these equations, I have already used the fact that the initial value of x, that is x1, is 0, y1 is 0, which also we have already used. Now, in the solution there is one unknown constant, which is r, and we have one condition here at this point, which can be used to calculate the value of r. Okay. Now, you can see that quite clearly. If I had a wire in this shape, this particular case, the bead will actually travel below y2, turn back upwards and go to y2, and this still would be the shorter path, shorter time path compared to the straight line path. Straight line path, remember, again is the shortest distance path, but that is not the case here, and that is very obvious because here the gain in the speed is much slower than the gain in the speed in this case, and in which case of course the ball travels the distance much faster than the shortest distance path. Okay. After this, I will do one more example, and that is again a very surprising and nice example, but that also tells you that this particular method, when we were deriving the condition for extremum values of functional, we automatically assumed that the paths are continuous paths. What if the path is not continuous? In which case we actually do not get the solution that we want, and that is the next example, which is minimum surface area of surface of revolution. In this example, what we want to find is the minimum surface or minimum area surface of revolution. By surface of revolution, what I mean is this: suppose you are given a curve like this in 2 dimensions, okay, and then you take this curve and turn it about x axis to make a 3-dimensional figure, and then you get a surface, and we want the surface area of that figure. So, when I rotate that figure, it would look like this. So, in this case, the shape that this curve generates is that of some kind of a flower pot. Now, if you change the curve, you will get a different surface. For example, if I just take a straight line, then I would get a cylinder. If this straight line is inclined and one of its points touches the x axis, then you will get a cone. Okay. And the third figure that we have already seen is you can generate some kind of flower pot or a vase. Now, the problem posed is like this. So, we have x axis, and on this x axis we have these 2 points, minus x naught and plus x naught, and we will fix these heights to y naught and y naught here, and we want to find a curve between these two, okay, such that when I construct a surface of revolution, its area should be minimum. So, what would be that curve is the question. Now, this is we can start by instinctively thinking about the solution. One of the solution is, of course, the surface area will be length of the curve at one point. Say, if I take a small elemental curve ds, which is at a height of y, then its that particular ds area would turn around and make a strip, and the area of that strip will be 2 pi y times ds. Now, what must happen to get a lower area is, if I start with a cylindrical solution, that means I just join minus x naught y naught and plus x naught y naught by a straight line, I would get a cylinder. But we know that if I sort of curve that cylinder inward, then area is likely to drop. But then if I take a curve like this, the area is likely to be smaller than that of a cylinder. But I should not go too far below, because as I go down on this curve, the length of the curve is also increasing, which means there will be some trade off between length of the curve and the area generated. Okay, so, probably the solution is somewhere in the middle. Now, there is one more solution. One more solution would be something like this, which I will draw separately here. So, this is your y naught, the height, and in this solution, what I will do is I will straight away drop down and take this curve. This curve is passing along the x axis here, which means when you rotate this and construct a surface of revolution, what I would simply get is two discs on the side of radius y naught, and they are connected by a extremely thin or cylinder of 0 surface area. And what would be the net surface area in this case? That will be, each of the discs on the side will have pi times y naught square as area. So, this will be 2 times pi y naught square. And see what happens. This solution, where you have a square graph like this solution does not depend on the separation between the 2 points, that is, it does not depend on x naught at all, which means if I increase x naught keeping y naught fixed, quite obviously this solution is going to win in the end. This area of any of these curves will definitely grow with x naught. However, the area of this curve here does not grow, in which case that will remain a minimum surface if x naught is very large. Now, let us try finding the solution here. So, what is the area of the curve, area of the surface? So, area of the surface will be given by 2 pi integral from minus x naught to plus x naught, and remember the area of the strip was 2 pi y times ds, and by now we know how to write ds, that is nothing but 1 plus y dot square to the power half dx. And this immediately allows us to identify the integrand. So, the integrand function, which is function of y dot and x, this is equal to y times 1 plus y dot square to the power half. And you can immediately see that this is independent of x, which means we can immediately use Beltrami identity, and that means this gives g minus y dot times dg by dy naught. This must be equal to some constant, and I will put that constant as a. and we can do this calculation. So, this will be y times 1 plus y dot square to the power half minus this will be y dot square into y divided by square root of y dot square. And you can of course immediately simplify this, and the simplification would be this would be a square times 1 plus y dot square must be equal to. So, here y times y dot square will get cancelled, and what you are left with is just y. Okay. So, that would become y square, and this gives us, so y dot is equal to square root of y square minus a square times 1 over a, and we will write this as, so this is dy divided by square root of y square minus a square, and this must be equal to dx by a, and this immediately gives us solution, and that solution is, so y must be equal to a times cos h into x minus b by a. Okay. The solution is very clear here, the integration is straightforward. Now, if you look at the initial conditions, we immediately see that b must be clearly 0, because the diagram is very symmetric. It is from minus x naught to plus x naught. So, the diagram will be symmetric. So, what kind of solutions are possible? If you remember the curve for cos h, the curve for cos h looks like this. It goes through a minimum and something like this, and at x is equal to 0, cos h is 0, which means this value here must be equal to a. Okay. So, it drops down. Now, from here what do we do? One of the constant b is equal to 0 has already been decided, because there is a symmetry in the figure. The second constant a we will decide by putting the condition on one of the endpoints. Now, it turns out, and I will include this in assignment for you people to do, but it turns out that for x naught and y naught, for not all values of x naught and y naught, you have a solution. So, you have no solution for, so if x naught by y naught is greater than roughly 0.66, then there is no solution. That means all the curves of course exist, but there is no curve at which area is stationary. That means, if you move that curve a little bit, then the area does not change. So, there is no stationary solution. If you want, we can make that very clear here, no stationary solution. Okay. And for x naught by y naught less than 0.66, it turns out at that critical value you will have one solution, but as soon as you fall below this critical value of 0.66, there are two solutions. Okay. So, two stationary solutions. Which one of them is minimum and which one of them is maximum, we have to decide by actually calculating either the second derivative or looking at the variation about these stationary points. So, I will describe these two solutions here, and I will ask you people to work these out in the assignment. So, the solutions look like this. There are two solutions, both are cos h type, that means both of them have this dip. One I will call it as shallow solution, and the other one is deep solution. And you can probably, just by looking at the figure, it is very easy to see that the shallow figure has a minimum and deep is actually maximum there. And if you look at the comparative solutions for all three of them, so what I have done here is plotted the area for each one of those solutions at x naught by y naught is equal to, so x naught and by y naught is plotted on x axis, and on the y axis you have area, and you can see that the shallow solution actually is the minimum solution. The deep solution, this one, is in fact the area is higher, and the green line which you see there, this one is the Goldschmidt solution which we earlier considered. This is basically the area as you change x naught by y naught does not change, and it turns out that somewhere near 0.5 for x naught by y naught greater than 0.5, I think 0.51, and of course less than 0.66, the Goldschmidt solution actually gives you minimum area. Now, the question we are going to ask is this: why is it that our calculation did not give us the Goldschmidt solution? The answer is very clear. Remember, while deriving the or doing the variational calculus, we implicitly assumed that the paths were not just continuous, but differentiable. In fact, we said sufficiently differentiable. So, this solution here, Goldschmidt solution, is not differentiable at this point. So, these solutions of course are not covered by the variational calculus, where we assume the path to be differentiable. Okay. So, these are the three examples we have seen. Now, of course, we will return to the mechanical systems and look at the Hamilton's principle, and from Hamilton's principle we want to show that we can derive Lagrange's equations, which means these two formalisms would be equivalent to each other. Okay. So, in Hamilton's principle, or before going to Hamilton's principle, I will generalize this variational calculus to many variables, many dependent variables. So, if you have a functional j which now depends on several y n, and this is integral from t1 to t2, but now integrand is function of y1 up to yn, then y1 dot up to yn dot and t dt. So, here of course, I have immediately I have made some changes. Instead of x, now I am writing independent variable as t. Okay. And this is we want to find the extremum of this functional. The trick that we do is exactly same as what we did in case of the one variable. So, for each variable y I will make a small variation which is epsilon times eta I. Remember, for each variable I now have a new function eta I, okay, and each of these eta i's can be different from each other. Okay. So, y I dot will be y I dot plus epsilon times eta I dot. So, clearly delta y I is epsilon times eta I, and delta y I dot will be equal to epsilon times eta I dot. And let us calculate the variation in the functional. So, delta j now is equal to integral from t1 to t2, and what we put here is a delta f, and delta f now can be written as, so summation over I, then partial derivative of f with respect to y I into delta y I, but delta y I is nothing but epsilon times eta I. So, I will put that epsilon outside and plus partial derivative of f with respect to y I dot into d by dt of eta I dt. And we of course will use the same trick again, integrate by parts the second term, and remember each of this eta I must be 0 at the end points, which means when you do integration by part you get a surface term, and the surface term will be 0 because you have eta which is, or each individual eta I which is 0 at the boundary points. So, this again will simply come out to epsilon times integral from T1 to T2, and then you have summation over I, and this will be del f over del y I minus d by dt of del y I dot times eta I dt. Okay. Now, this must be 0 for every arbitrary eta I, for every eta I, and not only that, eta 1, eta 2, eta 3, these are all independently or can be independently chosen. So, one of the things we can do is in fact choose eta 1 is equal to 1 and all the remaining etas to be 0, and then the simple calculus tells us that for each I del f over del y I minus d by dt y I dot must be equal to 0. There we go. So, in case of a Hamilton's principle, all that is going to happen is J is nothing but action, and the integrand function f is in fact the Lagrangian, and we write this as function of q, q dot and t, which is a short form for q1, q2 and so on, in which case for each I get del L over del q I minus d by dt q I dot must be 0, and these are nothing but the Lagrange's equations. Okay. So, what we have shown here is that the Hamilton's principle implies Lagrange's equations. So, the statement of the Hamilton's principle, of course, we will modify a little. Instead of saying the principle of least action, the principle now modifies that the natural system or a mechanical system would choose a path which is stationary, instead of saying minimum, stationary with respect to the action. Okay. So, what we have seen here is that Hamilton's principle implies Lagrange's equation. We also have to do the inverse proof, which is starting from Lagrange's equation, we have to prove the Hamilton's principle. That of course, I will leave it for you people to do. Now, what I will do is, from this point onwards, we want to see whether the Lagrange's equations give us the conservation laws which we obtain from the Newtonian mechanics or Newton's equations. But see, the Lagrange's equations in fact have lot more information in it. It is you can the best thing that can happen with the Lagrange's equations is you can do arbitrary coordinate transformations, and the general form of the Lagrange's equations remains same, and this is what we are going to look at in the next section.